Assalamualaikum warahmatullahi wabarakatuh, and hi. In this video we will look into heat conduction example. Heat conduction in a plane wall. Consider a large plane wall of thickness L equals 0.2 meters, thermal conductivity K equal 1.2 watt per meter Kelvin, and surface area A equal 15 meter square. The two sides of the wall are maintained at constant temperature T1 equal 120 degrees C and T2 equal 50 degrees C respectively. Determine A. The variation of temperature within the wall and the value of temperature at X equals 0.1 meter, and B. The rate of heat conduction through the wall under steady conditions. Before we can solve this problem, we need to make a few assumptions. Assumption number 1, heat conductivity is steady, because in the question they not mention anything about time. And assumption number 2, heat conduction is one-dimensional since the wall is large relative to its thickness, and the thermal conditions on both sides are uniform. And assumption number 3, thermal conductivity across the plane wall is constant. And number 4, there is no heat generation, because we don't get any information about heat generation from the question, so we assume there is no heat generation. The first strategy to solve this problem is to set up the governing equation. Taking the direction normal to the surface of the wall to be the x direction, the differential equation for this problem can be expressed as d squared t over dx squared equal to 0. So we have differential equation here, which is linear and second order. So we need two boundary conditions related to x to solve t. So we need two boundary conditions. From the question, we can get both boundary conditions. Boundary condition number 1 is t at point 0 equal T1 equal 120 degrees C. And boundary condition number 2, T at point L equal T2 equal 50 degrees C. Integrating the differential equation 2 times, we get the general solution for this question, which is Tx equal C1x plus C2. C1 and C2 is constants that came out from the integration process. Now we apply boundary condition 1 to the general solution. We will get T0 equal C1 multiplied by 0 plus C2, which will be C2 equal T1. And apply boundary condition number 2 to the general solution, we get TL equals C1L plus C sub 2, and we can rearrange this equation T2 equals C1L plus T1, because we know T1, C2 is equal to T1. And we rearrange in terms of C1 equal T2 minus T1 over L. Now we have the value for C1 and C2. So we substitute those values or expressions into the general solution. We will get Tx equal T2 minus T1 over L x plus T1, which give us the general expression for temperature distribution. Next, we substitute the given information inside this equation. We will get T, because we want to calculate T at 0.1 meter. So T at 0.1 meter equals 50 minus 120 degrees C over 0.2 multiplied by 0.1 meter plus 120 degrees C. We'll get the temperature of T at 0.1 meter is equal to 85.85 degrees C. Next, for question B, we want to calculate the rate of heat conduction. So the rate of heat conduction anywhere in the wall is determined from Fourier's law, which is Q dot wall equal minus Ka dt over dx. And we can if we integrate dt over dx, we will get C1. So this equation will be Q dot wall equal minus Ka C1. So now we know C1 is equal T2 minus T1 over L. We substitute the C1 expression, we will get minus Ka T2 minus T1 over L. And we can rearrange this expression or equation to remove the minus sign at the beginning of the expression by multiplying it into this. So we get Ka T1 minus T2 over L. Then we substitute all the given values inside this equation. We will get Q dot equal Ka T1 minus T2 over L, which equal to K given in the question equal to 1.2 watt per meter Kelvin. Area is also given in the question, 15 meters squared, and T1 is given in the question, 120, and T2 50 degrees C over L equal to 0.2 meter. We will get Q dot, or the rate of heat conduction, is equal to 6,300 watt. Thank you very much. We will see you again in next video.